start the recording here. So section 3.2 is the product and quotient rules. Okay, and let me give you a moment to copy down this formula. This, by the way, is called this is known as the product rule. Okay, I'll give you a moment to copy that down. Okay, so this is the product rule. And what you're doing here is you are, of course, when they say if f and g are both differentiable, they mean that you can take derivatives of the functions f and g. And they're saying that if f and g are differentiable, then the derivative of the product f times g is going to be equal to the function g times the derivative of f plus the function f times the derivative of g. That's called the product rule. And we can denote that in briefer notation like this. Let me show you here. You can have f times g prime means you're taking the derivative. F g prime. There are different ways it's presented, but I like doing it like this. F prime times g plus f times g prime. How many kind of like this brief notation in terms of memorization of derivative rules? How many find it helpful? Okay, Shako, John, excellent. Ian, Anna, yes. Lynn agrees too. And I mean, you know, like for what we learned on like for section 3.1, if you were to use this brief notation, you'd have, you know, there you're learning that the derivative of a sum, so f plus g prime, Thank you, Sebastian. F plus G prime would equal F prime plus G prime. Okay, so another, thank you, Rodrigo. That's another, you know, just notation, just a quick notation. Now, you'll notice that with the product rule, they write it, they write it basically like this. Okay, so like here, the way they have it is on the left, they have the derivative of the product FG, so that's the same as FG prime, equals, now they have G first times F prime plus, for the second part of the product rule, they have F times G prime. But you'll notice that, is everybody okay? What I'm doing is I'm taking the product rule as they show it here using the Leibniz notation and simply rewriting it using the Newton notation. That's all I'm doing. Is everybody okay with that? Are there any questions? Maybe give me a thumbs up if you're comfortable, maybe a few of you. That would be nice. Okay, thank you. Excellent, excellent. Well, so the thing is, see, if memorizing the product rule, for me, it's much easier. Thank you, Rodrigo. It's much easier to have things in order. Excellent, Sebastian. Excellent. So, you notice how I write it. I have F prime G plus F G prime. It just seems easier to remember the product rule in that form than this other form, G times F prime plus F times G prime. But that's just me. But just keep in mind that, like, when you look at, like when you're working on your homework for section 3.2, and maybe you're looking at one of the help videos, they likely will use this form here for the product rule. But you don't have to use that form. You can use my form, my preferred form for the product rule, and WebAssign would take the answer, even if your order is a little different than theirs. So it's okay. Okay, so let's prove this rule. Let's prove this rule so that you appreciate the rule. So what I'm going to do is I'm going to let Betsua, who likes my form a little better? Betsua does. Okay, Nicholas. All right, people are different. People are different. Okay, Rodrigo, very good. John and Sebastian, wonderful. Okay, okay, thank you. Well, to prove the rule, I'm going to define my product, FG, as my big H function. Thank you, Shako, my big H function X. Then H prime of X, H prime of X, using the definition of the derivative, will be the limit as little h goes to 0 of big H of X plus H minus H of X over H. Okay. Now the book, incidentally, when they proved the product rule, they use a different proof. They use these what are called like differentials, deltas, delta x's, delta u's. But I think my proof is going to be a little easier for you. So you don't need to worry about this right now, the delta x, delta u. Okay, so then what we have to do, well, John, you'll delta, sometimes it's helpful. The different notations are helpful in helping you understand problems in different settings. Okay, that's really where they come in handy. And you'll learn a little more about deltas. You'll see them a little bit later in the course. You'll see them a little more later, like in section. Let's see. I believe section. Let me see. Did we cover that? Let me just check one thing. I'm looking on the syllabus to see if we cover this particular section. Yeah, like section 3.8, the delta notation is used a little more often. But for right now, we're good with this. All right, very good. And, okay, well, big H of x plus h would be f of x plus h times g of x plus h. That's fine. And then, I'm going to do a little trick here. Now, here's a little trick. The book doesn't show you this trick, but I'll show it to you. What I do is I add a term, f of x times g of x plus h. But then I subtract the term. So because I'm adding and subtracting this term, and you'll see why we're using that term, because I'm adding and subtracting the term, the limit, this limit here, is the same as the limit above it. But there are advantages to putting in that term, because what's going to happen is I'm going to regroup the numerator. I'm going to regroup it. I'm going to bring over the minus f of x times g of x plus h term. I'm going to bring that over here. Okay. I'm going to bring that over here. And then the f of x times g of x plus h term, I'm going to bring that over here. And the reason we want to do that, is because then for this right here, that expression there, I can factor out the g of x plus h from both terms. It's a factor, common factor. And so I can write this expression in the blue box. I can write that as g of x plus h times f of x plus h minus f of x. Similarly, this expression here, f of x times g of x plus h minus f of x g of x, I can factor out the common factor f of x. And so the expression would become f of x times g of x plus h minus g of x. Are there any questions up to this point here? So of course we're finding the derivative of the product, which we represent by capital H, product of f and g. Okay, well now what we can do is we have here a plus, right? We have a plus here. And so I can split this fraction up into these two fractions. This fraction the limit of that fraction, plus this other fraction. If you think about it, it's easier probably to think about going from the next step to the previous step, because the limit of and you have a sum here, right? There's a plus there. The limit of a sum, the sum of two limits, if the limits both exist, is the limit of the sum. And the limit of the sum is what you have here. But what we're doing is we're taking the limit of the sum and just breaking it up into the sum of the two limits. That's what's going on. But now what's beautiful is you can compute this limit here and this limit here as the first limit as h goes to 0 would be g of x times f prime of x. The second limit as h goes to 0 would be f of x times g prime of x. And you've solved, you've proven the result, you've proven the product rule. Yes, I agree, Nicholas. This is, I mean, I remember when I took Calculus 1 in college, I thought this was like some of the coolest, I mean, it was like my favorite class, you know, just because of seeing cool stuff like this. So now we've proven the product rule. We've proven it. Are there any questions at all? All right, may we move on? Is everybody? So, you know, the G of, I'll just make a comment here. Let me see here. I want to maybe have this. The G of x plus h, as h goes to 0, G of x plus h is going to go to G of x. And then the f of x plus h minus f of x over h, as h goes to 0, that's going to go to f prime of x. Similarly, for the second limit, as h approaches 0, well, f of x isn't dependent on h, so that's just going to stay f of x. But then the limit, I mean, f of x can actually be brought out in front of the limit, right? And so what you're left with for the second part is the limit as h goes to 0 of g of x plus h minus g of x over h. And that's going to then go to g prime of x. All right. John, you're good? All right, excellent, excellent. All right, so then we've established then, in short notation, we've established the product rule. But also we need to take derivatives of quotients. So there's a rule for the derivative of a quotient. F over g prime is going to equal f prime g minus fg prime over g squared. That's called the quotient rule. And we're not going to prove that. We're going to let that go. Maybe we'll have a chance to prove that, you know, another day. But let's take it on faith for now, so that we can get to some examples. But now with you know, we can take the derivative of a sum. This is g squared on the bottom, Ian. This is g squared on the bottom of the quotient rule. Yep, that's right. So we're able now to take derivatives of sums and differences and products and quotients. Okay, and many of the functions you've learned about are can be written as sums of functions, products of functions, or quotients of functions. You know, a rational function is a quotient of two functions. So now with these rules in hand, we are able to apply them to a variety of functions where we can compute the derivatives. Okay, and of course we want to get to those examples. Are there any questions? All right, Lynn's good, Nicholas is good. All right, very good, Rodrigo. Well, and Anna, let's go ahead and then move to an example. So let's find the derivative of a product first. So this function f of x is a product of a polynomial and an exponential function. Let me give you a moment to copy that down. Okay, so what derivative rule do we use here? What's the rule we're going to use called? The product rule. Very good. All right, well then let's go ahead and apply it. So f prime of x is the derivative of my product. There's the product. And the first function, I'll call that f. I mean, I don't need to have like this as part of the work, but I'm just, since it's your first time taking the derivative of a product and the product rule is new to you, I'm gonna, try to justify everything that's going on here. So I'm taking the derivative of a product. And we know the product rule. So the derivative of f times g, or fg prime, equals f prime g plus f of g prime. We derived that rule. So in the first step, what I do is I say, okay, well, x cubed plus 2x prime, that's f prime. E to the x is just g, plus, now, x cubed plus 2x, that's just f, and the derivative of e to the x, that's g prime. Okay. So there are different ways to write out the product rule. You could use, for instance, Leibniz notation if you wanted. But I think you know, sometimes the to me this takes little effort to write the product rule this way with the primes. And so that's what I do. Now x cubed plus 2x, that's a polynomial. What's the derivative of x cubed plus 2x? That's right, Lynn, 3x squared plus 2. Okay, well, 3x squared, but then the derivative of 2x is 2. What's the derivative of e to the x? Good, e to the x. So, very good, everybody. So then, here we are. And therefore, f prime of x, right, this is what we're finding. The derivative of my function x is equal to this expression. 3x squared times e to the x plus 2 times e to the x plus x cubed times e to the x plus 2x times e to the x. And what I'll do, I mean, WebAssign would accept this answer, but there's nothing wrong with factoring out an e to the x from all these terms. It's less to type in WebAssign. And of course, since the function is with respect to x, the derivative is with respect to x. So, you know, naturally, in these homework problems, you're having different variables like t and you know, maybe theta and all these different independent variables. But so you have to be you know, correct with your variables and your notation. But there's the product rule. Are there any questions on that? All right. Shall we go to the next example? Everyone's comfortable? All right. Well, we did the derivative of a product. Now let's do the derivative of a quotient. Okay. Take a moment to copy this down. Okay, so we're going to use the quotient rule on this. So let's just go ahead right to the solution. I mean, really, we're just applying the quotient rule. Clearly, this is a quotient. So this is our quotient rule. You notice how I'm very careful with notation when I work these problems. There's no reason to, you know, be sloppy with notation. You want to use good notation. You want to use equal signs, and you know, using proper notation shows confidence in your work. How many maybe have noticed just from the math that you've already done that when you're you know, maybe if you weren't as good at math as you wanted to be, but now you're better at math. How many notice when you got better at math, your notation improved? Did any of you have that experience? I did. Okay, Nicholas knows what I'm talking about. All right. A bit more organized. That's right, Lynn. That's right. Shako agrees. Absolutely. So, okay. Well, so the derivative of my capital of f of x function is using Leibniz notation. It's d dx of this quotient. And we have an f function on top and a g function on the bottom. And so there's nothing to it but to do it, as they say. So you've had practice already taking derivatives of polynomials. So I just, you know, wrote down the result here. But let me know if you have any questions. I'm pleased that many of you worked through the assignment that was due today. That's good. And see, I like to pace my assignments, because now that, how many find that is helping you understand this lesson a little better? The fact that you worked on section 3.1 already. I'm sure there must be a few people. Okay, Anna, Betsua, Trevor, absolutely. Rodrigo, Joe, that's right. And really, you become, you know, a more efficient learner too. You know, when you become a more efficient learner, and you're more comfortable with what you're learning. You know, instead of trying to learn it all at once. You know. All right, but let me let you copy this down, and let me know if you have any questions. I'll denote a few things here. Oh, okay. So what I did, by the way, I did this a little differently than the last problem. So this here, 4x cubed minus 5 times 3x squared plus 1/2 x to the negative a half, that's f prime. X squared's g. And then we subtract the function f, little f, which is x to the fourth minus 5x cubed plus x to the half, and then multiply it by 2x, which is g prime. And then, of course, we're going to divide by g squared. So here what I did was I skipped the intermediate step where I have like the terms that are prime. I just take the derivatives and apply the rule. Are there any questions? Okay, now would you want to type this whole thing in WebAssign? This whole answer here. Well, Lynn, that's good, but you could simplify your answer, right? And on your next exam, I may want to answer simplified. I may specify that. Yeah, so why not multiply the x squared here? You know that the f prime times g portion, you're going to take x squared and distribute it to those three terms. And if you do that, you'll get 4x to the fifth minus 15x to the fourth plus 1/2 x to the 3/2. X to the negative 1/2 times x squared. Of course, you add the exponents. That gets you x to the negative 3/2. Likewise, I'll distribute the 2x to the f function, x to the fourth minus 5x cubed plus x to the half. And then don't forget, we got a minus here as well. Let me see. Do I maybe have an error? Hold on here. Question, one moment. John asks, why is it minus 5 times 3x squared? So what I did when I took the derivative, of the 5x squared, 5x cubed, by the constant rule, a constant, hold on. I want to make sure I'm saying the rule correctly. I believe it's the constant, yeah, the constant multiple rule. The 5 just factors out. And then you take the derivative of x cubed, which gets you 3x squared. That's what we did there. So I distribute now here, going to the next step here, the 2x, like I'm talking about this part right here. Distribute the 2x to the x to the fourth, the negative 5x cubed, and the x to the half, right? These three terms. But then don't forget about the minus in front, and you will get negative 2x to the fifth plus 10x to the fourth minus 2 times x to the 3/2. It's just math, class. It's just algebra. And then we can combine some like terms on the top, right? We can combine some like terms here. 4x to the fifth combines with negative 2x to the fifth to give you 2x to the fifth. Negative 15x to the fourth combines with positive 10x to the fourth to give you negative 5x to the fourth. And then finally, you have a half times x to the 3/2. That combines with the negative 2x to the 3/2 to give you negative 3/2 x to the 3/2. And we can even do a little bit better than that. We have this x to the fourth in the denominator. Let's divide it through. And when we do that, we'll get our final answer for our derivative of this quotient. Okay, we'll get our final answer. The derivative of the quotient is going to be 2x minus 5 minus 3/2 times x to the negative 5/2 power. Okay, that's what big F prime of x is. So what I try to do in the homework is I provide a variety of exercises to reinforce these concepts. In truth, I could assign more WebAssign exercises than I do, but I look at every problem that I assign. I try to be careful what I assign, understanding that it's work for you to do every problem. So every problem I give you, I try to make sure it's like a valuable problem. so to speak, because I know what's coming down the road for you, you know. After calculus 1, you have calculus 2, right? So, but are there any questions on this problem? Who likes the quotient rule? Okay, Nicholas likes it. Shako likes it. Very good. Great. Lynn likes it. Ian, I think, likes the product rule, power rule. So everybody has kind of their favorite rules. Now I'm going to point one thing out here on this problem. Anna likes the product rule more. I understand. This problem, actually, there was a second way to do it. We applied the quotient rule right away, right, to our big f of x function. But you could have divided the x squared into each of the 3 terms on top to get that the big f of x function simplifies to x squared minus 5x plus x to the negative 3/2. And then when you take the derivative of big F of x, you'll get 2x minus 5 minus 3/2 times x to the negative 5/2. So it took a few less steps. Yeah, Lynn likes that. Well, and it is much better, Lynn. So when you're doing your homework, sometimes they'll give you rational functions where you can do stuff like that. But of course, it won't happen all the time, right? So are there any questions at all on this problem? All right, let me stop the recording.